Welcome to Podcast Learn and Fun. Let's start today's journey of learning. Today we're venturing into the fascinating realm of quantum mechanics, exploring something called coherent quantum states. You might be wondering what makes these states so special.
Well, imagine a quantum system behaving like a well-behaved classical harmonic oscillator. It's a bit like finding a hidden bridge between the unpredictable quantum world and the predictable physics we see every day.
Okay, that's a cool image. So to dive deeper, let's refresh our understanding of the quantum harmonic oscillator, the QHO. It's our foundation for understanding these intriguing states.
Think of the QHO as a system with energy levels arranged like rungs on a ladder. A particle in the system can only occupy specific energy levels, not in between. And this discrete nature of energy levels is key to understanding the oscillatory behavior of coherent states.
So if I'm picturing this right, we've got our ladder of energy levels, and these coherent states somehow sit on those rungs. But how do they actually fit into this picture?
Coherent states are like special combinations of these energy levels, almost like a recipe where you blend different energy levels together. And what's unique is that they act like eigenstates of the annihilation operator.
Hold on. Annihilation operator. That sounds a bit intense.
Yeah.
What exactly does that mean in our ladder analogy?
Good point. The name can be a bit misleading. It's not as dramatic as it sounds. Think of it as a step-down operator on our energy ladder. When it acts on a state, it lowers its energy by one step, bringing it down a rung.
All right, so it's like our operator can move these states down the energy ladder, but why is this annihilation operator so important for coherent states?
The key is that when you apply this operator to a coherent state, the state itself doesn't fundamentally change, it's just multiplied by a number. This means coherent states maintain their unique shape or coherence over time. They don't spread out or become unpredictable like some other quantum states.
So they're like those perfectly formed ripples in a pond that hold their shape as they travel outward. That's really different from the quantum fuzziness we often hear about.
Exactly. It's one of the reasons they behave so much like those classical oscillators we talked about. They hold their form and evolve predictably, like a swinging pendulum or a vibrating string, even though they live in the quantum world.
Okay, my mind is officially blown. So we've got these special states that are like a blend of energy levels. They hold their shape over time.
Yeah.
And they act almost like classical systems. But how do we actually create these coherent states mathematically? Do we need to go full-on physics equations here?
You actually don't need to delve into complex equations to get the idea. Remember those ladder operators we talked about? The creation and annihilation operator. There are tools for navigating these energy levels.
Right. The annihilation operator moves us down.
Yeah.
And the creation operator bumps us up the energy ladder. So how do we use them to build a coherent state?
Imagine starting at the very bottom rung of our ladder, the ground state.
No.
Now picture applying the creation operator repeatedly to build up the state, but each time you multiply it by a complex number. And you keep doing this, adding a little bit more oomph each time, infinitely many times.
So it's like we're carefully layering on these energy levels, building up the state in a very specific way, using our complex number as a sort of quantum spice to get the recipe just right.
That's a great way to think about it. And this infinite sum, this precise combination of energy levels created by the repeated application of the creation operator with that special complex number twist, gives us a coherent state. It's like a carefully crafted quantum cocktail. So we've got these coherent states, these carefully crafted combinations of energy levels, and one of the most striking features of these states is their ability to minimize uncertainty. Remember Heisenberg's uncertainty principle.
Right. It's like trying to catch a shadow.
Yeah.
The more you try to grasp one aspect, the more elusive the other becomes. It feels like there's always this inherent fuzziness when you're trying to measure things in the quantum world.
Exactly. But here's where coherent states come in. They actually achieve the minimum possible uncertainty allowed by Heisenberg's uncertainty principle. They're like the ultimate precision instruments in the quantum world, getting us as close as physically possible to knowing both position and momentum.
Whoa, that's pretty mind-blowing. But how do they actually pull that off? Does it have something to do with that special recipe we were talking about? The way they're built from those energy levels?
It's precisely because of their unique mathematical structure. Remember how we described coherent states as these special superpositions of energy levels, constructed through the repeated application of a creation operator? Well, it turns out that this specific combination of energy levels crafted through that process naturally leads to minimized uncertainty.
So it's like the recipe for coherent states has built-in uncertainty minimization. It's like they're designed from the ground up to be the most precise representation of a quantum state. as precise as the laws of physics will allow.
Exactly. And this minimum uncertainty property further reinforces their classical-like behavior. Remember, classical objects have well-defined positions and a momenta. Coherent states come the closest to mimicking that in the quantum realm.
Okay, this is all starting to click now. So coherent states minimize uncertainty, they evolve predictably over time, and they closely resemble classical oscillators. But is there anything else that makes these quantum objects so remarkable?
Well, another fascinating aspect is the concept of overlap between different coherent states. Remember how we talked about them having parameters that are kind of like their locations in a quantum sense?
Right, like coordinates in a quantum space.
Exactly. The overlap between two coherent states tells us how similar they are, how much they match up in terms of their properties.
So it's like a measure of their closeness in this quantum space.
You got it. And here's the interesting part. The overlap between two coherent states depends on the distance between their parameters in this quantum space.
So the closer their parameters are, the more they overlap.
Precisely. Think of it like two ripples in a pond. If their centers are close together, they'll have a large overlap, meaning their wave patterns blend significantly. But if their centers are far apart, their overlap will be small, meaning their wave patterns remain largely distinct.
That's a great analogy. So the overlap gives us a way to visualize how similar or different these coherent states are from one another.
Exactly. And this concept of overlap has some interesting implications. It helps us understand how different coherent states can be combined to create new quantum states.
So it's like we can blend these quantum ripples together to create new and complex wave patterns.
Precisely. And this ability to combine coherent states is one of the key reasons why they're so useful in things like quantum information and quantum computing.
That makes sense. It's like having a set of building blocks that you can mix and match to create an infinite variety of quantum states.
Yeah.
All thanks to this idea of overlap.
Exactly. And this ability to combine coherent states, understanding how they interact with each other, is crucial for manipulating and controlling quantum systems, which is a big part of what makes them so powerful.
It's like we're starting to unlock the secrets of a hidden language, a language that describes the universe at its most fundamental level. It's pretty mind-blowing. Welcome back to Podcast Learn and Fun. We've been on quite a journey exploring these fascinating quantum objects called coherent states. We've seen how they bridge the gap between the classical and quantum worlds, minimizing uncertainty and evolving in these predictable wave-like patterns. But I'm really curious to see how these seemingly abstract concepts actually show up in the real world.
Well, one of the most striking examples is the laser. Think about it, lasers are everywhere. From barcode scanners and laser pointers to medical devices and fiber optic communication systems, they're an essential part of our modern world.
It's amazing to think that something as commonplace as a laser pointer is based on these mind-boggling principles of quantum mechanics.
And at the heart of a laser's operation are these coherent states we've been discussing. The light emitted by a laser is in a coherent state, which means the light waves are all oscillating together in sync. This is what gives laser light its unique properties.
So the laser's ability to produce such a focused, intense beam of light, it's all thanks to these synchronized light waves. All thanks to coherent states.
Exactly, because the photons in laser light are all in phase. They act in unison, reinforcing each other and creating this incredibly powerful and precise beam of light. It's like having a perfectly synchronized army of photons marching in lockstep.
That's a great analogy, and it really highlights how this seemingly abstract concept of coherence has led to one of the most transformative technologies in history.
And the influence of coherent states extends far beyond lasers. They also play a crucial role in quantum field theory, which is our framework for understanding the fundamental forces of nature, the very fabric of the universe.
So we're talking about some seriously big picture stuff here.
Absolutely. In quantum field theory, we describe forces and particles in terms of fields that permeate all of space. And it turns out these fields can also exist in coherent states.
So it's like the universe itself can exhibit this quantum coherence.
In a way, yes. For example, in quantum electrodynamics, which describes the interaction between light and matter. Coherent states are used to represent the electromagnetic field.
That's mind-blowing. So the light we see, the electricity we use, all of these phenomena are influenced by coherent states.
They are woven into the very tapestry of the universe, influencing the behavior of matter and energy at the most fundamental levels.
It seems like coherent states are not just a theoretical curiosity. They're a fundamental aspect of our physical reality.
And their importance continues to grow as we delve deeper into the quantum realm. For example, in quantum computing, coherent states are being explored as a potential way to represent and manipulate quantum information. They might even be the key to unlocking the power of quantum computers.
Wow, it sounds like coherent states have the potential to revolutionize technology as we know it.
Their ability to minimize uncertainty and evolve predictably makes them ideal candidates for handling and processing information in the quantum world. It's a fascinating area of research with incredible potential.
This has been an absolutely incredible journey. We started with the basic idea of a quantum harmonic oscillator and ended up exploring the vastness of the universe and the future of technology, all thanks to these remarkable coherent states.
It's been a pleasure sharing this exploration with you. Coherent states really showcase the beauty and strangeness of quantum mechanics and how those principles shape the world around us.
I feel like we've only just scratched the surface of this fascinating topic. It's clear that coherent states are more than just a theoretical concept. They're a fundamental part of our reality with the potential to shape the future.
Absolutely. It's a field that's constantly evolving with new discoveries and applications emerging all the time.
Well, on that note, we'll have to wrap up this episode, but I encourage all our listeners to keep exploring the world of quantum mechanics and the wonders of coherent states. It's a journey that will continue to surprise and amaze you.
It's a journey well worth taking.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.